All right, so this is an extension from 4.2 momentum. Specifically, I want to discuss the idea of collisions. Okay, so a recap of concept from last lesson. Momentum is denoted by, it's a vector quantity, it's denoted by the mass, answered by the velocity. Okay, we also determined that the change in momentum, okay, equals to force divided by change in time. So this means that in the absence of force, okay, then there's no change in momentum. All right, so this is an important thing to as we go into collisions. So in collisions, we know that if you have an isolated system, so let's just say that you've got two balls being thrown towards each other, okay, and afterwards they bounce off each other. All right, afterwards they bounce off each other. Okay, then but in the meantime, if there's nothing touching the system, there's no air resistance, there's nothing else that would put more force into, or there's no other force applied to either of the balls, only to each other, then the momentum, okay, the total momentum will be the same as the total momentum here. Now, this symbol is called summation. You don't need to know it's a mathematical thing, but just means that total of P, okay, P of body A and P of body B has to be 4 mass equals to total momentum of A plus momentum of B. Okay, there could be some mass exchange, or sorry, there could be some momentum exchange between the two, but in most of the cases, sorry, there might be momentum exchange between the two, but the total momentum should be the same. All right, so we're going to go through a few collision cases, okay? And most of the cases involve two bodies that they give you the initial conditions, and you need to determine the final conditions after a little while, okay? So we can use this to determine other things. So first case, okay? You have two trolleys, okay? So before you have this one here moving at a velocity and the other one is stationary. Okay, so before and afterwards, this one stop moving. Okay, and this one continues on. Okay, so this is the first scenario. So you look something like this. Okay, so you can see that if I play this again, this trolley stops. The first trolley stops, while the second one essentially in stationary before, and as I collide, the momentum and the kinetic energy is transferred into the second one. Okay, so that's the first case. Okay, and then we have second case is where when you have two of them both moving at a certain velocity. Okay, so and afterwards you're going to have both of them still moving in the same velocity. Sorry, in the same direction but different velocity. So there have been some momentum exchange. Okay, in fact, this is probably not an accurate diagram. So in order for this one to actually collide, the one on the right needs to move at a slower speed. Okay, now finally, we also have another case where you have one of them moving, the other one's not, or it's maybe similar to the one before when both moving in the same direction, but then they're going to collide. Okay, and afterwards, the two of them move together, which means they're actually stuck together at a certain speed. Okay, and this one here can be seen in this case here. Okay, so now each of these, because you are excluding the any external force, so momentum should be conserved. So that's something that we're going to exploit in our case. So mathematically, this is how we write down momentum conservation. Okay, so you got your mass of number one times by the velocity of the first, and I'm going to write a little b here with a comma. Okay, so this means that this part here is velocity before. Okay, now don't forget we're going to now add this to the second velocity, and again I'm also going to write b here. So that means it's a velocity before the collision. Now all of this is total, okay? All of this is total P before. Now all of this got equals to M1 V1 A plus M2 V2 A, okay? Where this is the velocity afterwards. Okay, so let's look at this a little bit closer together. So the momentum of body A or body 1 plus momentum of body 2 before mass equals to the momentum of body 1 and body 2 afterwards. Okay, no matter if we can assume momentum conserved, this is always going to be true. Okay, so to explore this, we're going to go through 3 examples, and I won't tell you which case we need to work it out ourselves. Okay, all right, so all right, first case. Trolley A with mass 3 kg traveling to the right with a speed of 4 meters per second. Trolley B has a mass of 5 traveling left at a speed of 6 meters per second. After the collision, trolley A rebounds with a velocity of minus 8.5 meters per second. Okay, and we assume this is an isolated system. We want to determine the velocity of trolley B after the collision. Okay, so let's actually draw the diagram to visualize what's going on here. Okay, so initially you got your trolley. One of them is going to a route with 4 meters per second, and the mass is 3 kilogram. Okay, and the other one is going in this direction here with 6 meters per second, and this one here is 5 kilograms. Okay, and this is before. Now afterwards, we learned that the trolleys are going to rebound. Okay, so this one here is traveling at minus 8.5 meters per second. Now mass should stay the same. And this one here, mass should stay the same, but we don't know where it's going or what direction it's going. Okay, so, and this is afterwards. So now we can use the equation as determined before to our advantage. So M1 V1B plus M2 V2B equals to M1 V1A plus M2 V2B. All right, so just to remind you, V1B and V1A are not the same because they're velocity before and after. So they're not the same. All right, so to go forward, we're substituting everything we know. So you got 3 kilograms times 4 plus 6, oh, sorry, 5 kilograms times. Okay, now note that momentum is a vector. Okay, so velocity is a vector. So if we define 4 to be a positive towards the right, then v2 before is 6 meters per second going the other direction. So this has to be minus 6. Okay, so just keep in mind that you need to keep the signs consistent. All right, now we know the mass don't change, so 3 times minus 8.5 as previously determined, plus 5 times V2B. All right, so doing a little bit of calculation, plus minus 30 equals to minus 25.5 plus 5 V2B. Okay, so I'll jump fairly quickly. You'll find that V2 equals to minus 1.5 meters per second. Sorry, positive 1.5 meters per second. All right, so let's visualize this for a second. So after the collision, so initially the two of them are going towards each other head on. After collision, the first body is going to rebound towards your left, and as a result, your second body here is now, based on a calculation, positive 1.5, is going to go in this direction, which makes sense. After collision, they rebound off each other. Okay, the next question asks you, determine whether collision is elastic. So we need to go through some definition quickly. Okay, so an elastic collision means your kinetic energy before must equals to kinetic energy after. Okay, so elastic means that you've had energy conservation. So even though we have momentum conservation, it doesn't actually mean that the energy is also going to be conserved. So we're going to check that now. Okay, so we use all the information we have because we have M1, we have all the masses and all the velocity. We can now do a calculation on energy. Okay, so part B, we need to look at the kinetic energy before equals to a half m1 v1 squared plus a half m2 v2 squared. Okay, and this is before, this is before. So this is going to give us a half times 3 times 4 squared plus a half times 5 times minus 6, minus 6 squared. Oh, come on. All right, and that will give you 144 joules. Know that we've mentioned once before that kinetic energy is a scalar. So even though I had negative velocity going the other direction, I'm going to end up with a positive energy. Okay, so I end up 144 joules before. Okay, so this is before. Now, EK after It's the same formula, other than the fact that you now have 1a plus a half m1 v1, so m2 v2a squared. Okay, so similarly, you got a half times 3 times minus 8.5 all squared plus a half 5 times 1.5 squared. And you find that all that also equals 144 joules. So you have EKB equals to EKA. Hence, it's an elastic collision. All right, so by definition, if there's elastic collision, there's also inelastic collision. So not all of the cases you're going to have the same same kinetic energy before and afterwards, and that's called inelastic collision. Okay, so we should see in the next couple of cases what this will look like. All right, so next example, and this one is from your book in question 13 in page 165. All right, so we've got a truck of mass 4 times 10 to the power 3 kilograms going in one direction and then going the other. So I'll get you to read that. So we need to show that the velocity of the trucks after collision 5.6 meters per second to the left. Okay, so first of all, it is a head-on collision again. Okay, and what we know is afterwards the two of them are traveling together. Okay, so it sticks to a smaller truck. Okay, so the two of them are going to travel together. So we're going to make a slight modification in our formula in order to conduct this question. So we still have m1 v1 b plus m2 v2 b equals to m1 v1a plus m2 v2a. All right, so this is our generic equation, but we know one thing, which is v1a equals to v2a. All right, so the reason is if the two trolleys are stuck together and traveling together like this, okay, then you know the two of them are traveling in this with the same velocity. So knowing this, my right hand side equals to m1 v1a plus m2 v1a because they're the same. And that allowed me to do a little bit of factorizing. So m1 plus m2 times by m1a is now my right hand side. Okay, so which means the momentum afterwards is the mass combined times by a shear velocity. All right, so I'm going to come back into the equation here, and I'm going to have 4 times 10 to the power 3 times 15 plus 2.8 times 10 to the power 3 times 35 minus 35, in fact, because it's going in the opposite direction. Yeah, okay, and all of that will equals to 4 times 10 to the power 3 plus 2.8 times 10 to the power 3, all multiplied by a shear velocity. Okay, so do the maths. You're going to end up with V combined, which is V1A equals to minus 5.59, and 2 sig figs is going to give me minus 5.6 meters per second. Now, The question here asks us to demonstrate that the collision is 5.6 meters to the left. Since I have a negative sign here, okay, that means since I've got a negative sign there, that means it's traveling in towards the left, since we define the right to be positive. Okay, it doesn't hurt if you start drawing this to begin with, so we know that positive towards the right. Okay, now I know for a fact that this one is an inelastic collision. We don't need to go through the, if you would like to, you can go through the calculation. And so that will show that the EK before doesn't equals to EK afterward. Okay, in fact, EK afterwards it's gonna be smaller than EK before. Okay, because you lost some energy in the collision. All right, so sometimes I call this one sticky collision, but we're just gonna stick to the fact that this is an inelastic collision. Okay, last question. Okay, two objects are traveling towards each other. Body A mass 20 kilograms travel towards the east, and the other one travel towards the west. So instead of left and right, we have east and west, no problems. After collision, you get the speed of one of them, you don't know the other one, so you got to determine it. Okay, so part A, let's lay out the questions that we have. In fact, let's draw it. So you got one object, let's call that body A. Okay, and this one here is going in one direction. The other one is going the other direction. All right, so initially the mass is going to be 20, mass is 30. Velocity is 14, and velocity is 10. And since it's going the opposite direction, we should write minus. Okay, so what we know, and this is before. Afterwards, afterwards, body A is going to rebound. Body B, we don't actually know what's going on yet. Okay, so doing the calculation as before, M1 V1 before plus M2 V2 before equals to M1 V1 after plus M2 V2 after. Okay, so you got 20 times 14 plus 30 times minus 10 equals to 20 times minus 12 plus 30 times V2A. All right, so the left-hand side sums up to be minus 20 equals to minus 240, oops, apologies. All right, so the left-hand side, you have 280 minus 300. So yeah, you got minus 20. And on the right-hand side, you got minus 240 plus 30 V2A. So V2A will end up being 7.33 meters per second. So this one here is going to go in that direction. All right, and part B asks you whether this collision is elastic. So part B, we're going to run through the kinetic energy equation. Okay, so kinetic energy before is a half mv squared plus a half m1 v1 before m2 v2 before squared. So that, going through the calculation, is going to give you 3,460 joules. This one here, the afterwards, 2,246 times 59 joules, okay, by applying a similar calculation. And you'll find that EKA is less than EKB, hence it's inelastic. Okay. Now, a common question is, now what happens if you have two trolleys? And one of them is stationary to start with. So we use the understanding that if it's stationary initially, there's no velocity, so velocity equals 0. So which means when you apply your momentum equation, then this term here, okay, this v here is 0, so this whole term cancel out. So you end up having only this to solve. Okay, and it will generally tell you at least one other information, such as what the velocity is after the collision for one of them, and you will already have the masses to determine this. Okay, so there's a lot of different combinations, and you should receive a worksheet on how to, a lot of different scenarios to solve through. Okay.